Alright, silly people, here's the situation. This time we're going to be finding the roots of this polynomial p of x, which is actually a normalized Legendre polynomial. But yeah, first of all, we're going to plot it on a matplotlib plot, and then we're going to use Newton's method to find the roots. So plotting it is pretty, routine at this point. Let's just get a matplotlib.py plot as plt imported. Define the polynomial p of x to be returning 924 times, in parentheses, x to the 6th minus 200, or 2,772 times x to the 5th plus 3,150 times x to the 4th minus 1680 times x to the 3rd plus 420 blaze it LMFAO times x squared minus 42 times x plus 1. Right, that's fine. And then we'll just create an input list from 0 to 1. That's going to be a linked space object, 0, 1, 1,000 points. And just plot XLS versus P of XLS and see what happens. Yeah, so that's going to be your Legendre polynomial, right? So to find the roots of this, again, we're doing Newton's method, so I'm just going to enter into this same code cell. What you need for Newton's method is you also need the derivative of the function that you're trying to find the roots of. Thankfully, this is actually just a polynomial, so we can very easily just do power rule derivative on this. So I think I'm even just going to copy down these terms here into the return line, but then this is going to be times 6 times x to the 5 times 5 times x to the 4 times 4 times x to the 3rd times 3 times x squared times 2 times x to the nothing minus 42. That was relatively painless, I think. But then Newton's method, I'm going to also define a function called newt, which is going to be a function of ex because I wanted to be fancy. You are going to, in here, define your accuracy. For the first time, Newman is having us be accurate to 10 decimal points, so the accuracy is going to be 1e minus 10. As always, going to set the error to an arbitrarily large number like Avogadro's number, and then get into the loop. So while the absolute value of the error is greater than the accuracy, you're going to go in here and you're going to say that the error is now equal to the function p of ex divided by the derivative of the function evaluated at ex. And once you calculate the error, you subtract off from your guess by the error, and whenever it hits the desired accuracy, you'll return the root. So now let's create a bunch of print lines where it's actually going to print all of the roots. So I'm going to call it x1 equals comma newt, and then we put in your guess for what the root is going to be. For the first one, I'm just going to plug in 0 because I don't think that there are any roots that are in the negative x domain. It's just going to be coming down from 0. And then I'm going to copy this print line down a bunch of times for the other solution. So like that for the 2nd, 3rd, 4th, 5th, and 6th roots. So the first root is taken care of here. The second root is going to be like around 0.2, I would think. Then this root is going to be around 0.4. Then this root is going to be around 0.6. And then this one is going to be around 0.8. And then finally this one is going to be, I'm just going to set it to 1. It'll work its way down to here from 1 for sure. But yeah, this should be pretty fast to run. It'll find the roots really quickly. Do I believe its results? So it's getting 0.03. That seems a little small, but I'll believe it. This is saying that that's 0.16. Sure. That's saying it's 0.38. Yeah. It's saying it's about 0.61. Yeah, that's fine. About 0.83. Sure. And then 0.96. Yeah, I believe it. So, okay, I think this is a code which works.